This research paper, titled Scaling Instruction-Tuned LLMs to Million-Token Contexts via Hierarchical Synthetic Data Generation, is authored by Linda He from Harvard University, along with Ju Wang, Maurice Weber, Shang Zhu, Ben Atiwaradkun, and C.E. Zhang from Together AI and the University of Chicago. The work focuses on overcoming the challenges that large language models, or LLMs, face when dealing with extremely long sequences of text, up to 1 million tokens. Large language models have made impressive strides in handling a variety of natural language tasks, but they often struggle with long context reasoning. This is due to two main issues. First, the computational complexity scales quadratically with the length of the sequence, making it resource-intensive, and second, there's a scarcity of high-quality, annotated data for long contexts. As a result, most open-source efforts haven't systematically explored or provided datasets that go beyond 100,000 tokens. To address this, the authors introduce a novel strategy for post-training LLMs using synthetic data generation. This approach is designed to extend the context window of these models efficiently, allowing them to handle much longer texts without losing performance on general tasks. The key idea is to create synthetic data that's hierarchical and scalable, meaning it can be generated for arbitrarily long contexts, even when real-world data is limited. The process begins with a pipeline for generating instruction tuning data. They start by taking a long document, such as a book, and breaking it down into smaller, manageable parts. This involves creating a pool of local summaries from the document. Then, they use an LLM as a QA generator to produce question-answer pairs based on these summaries. One important aspect is the locality-guided hierarchical summary sampling. This means they generate summaries at different levels of detail. For instance, they might create a full summary of the entire document and then more focused summaries for specific sections. This hierarchy helps in capturing both broad and detailed information. From here, they generate various types of QA pairs to train the model. Let's break these down. First, there's depth versus breadth QA generation. In this, the generator creates questions that relate to the full summary but require specific knowledge from a local summary to answer accurately. For example, given a context from a local summary and the overall book summary, the question might test deeper understanding that bridges the two. Next, they have hierarchy-aware QA. This involves using multiple summaries from different levels of the hierarchy. The generator acts as a professor designing a final exam, creating complex questions that demand analysis and synthesis across all the provided summaries. For instance, it might ask a question that integrates information from 3 different chunks of the document. Then, there's multi-hop QA, where questions require chaining information across the context. The generator uses the local summary to create questions about details, events, characters, or settings, ensuring the answer is directly derivable from the given information without external knowledge. Finally, they include local-specific QA and complex and diverse QA. Local-specific questions focus on precise details within a single summary, like temporal events or specific attributes. Complex and diverse QA expands this by generating a variety of question types, such as those involving timelines, comparisons, or hypothetical scenarios, all based on the context provided. This entire pipeline is illustrated in the paper's Figure 1. Which shows how they pool local summaries and use them to generate these QA pairs through a structured process. To train the models, the authors employ a step-by-step rotary position embedding, or ROPE, scaling strategy. ROPE is a technique used in transformers to handle positional information in sequences. Normally, it helps models understand the order of tokens, but extending it to very long contexts requires careful scaling. Their method involves gradually increasing the context length during training. They start with shorter sequences and progressively extend them, using the synthetic data to fine-tune the model. This step-by-step approach ensures that the model adapts without forgetting its general capabilities on shorter tasks. The results are promising. The trained model, which supports up to 1 million tokens, performs well on benchmarks like Ruler and Infinite Bench. Ruler tests long context understanding and reasoning, and the model maintains consistent performance as the context length grows. On Infinite Bench, which evaluates models on extended sequences, it shows robust results. Importantly, the model doesn't sacrifice performance on general language tasks, meaning it can still handle everyday queries effectively. This work highlights the practical applications of extending context lengths. For example, in company-wide document retrieval, models could analyze vast organizational histories. In legal scenarios, they could reason across multi-document datasets, like interconnected project timelines. This breakthrough addresses the gap in open-source resources, as no prior datasets exceeded 100,000 tokens for instruction tuning. By using synthetic data, the authors bypass the need for expensive, real-world long context annotations. This makes their approach scalable and accessible, potentially accelerating advancements in LLMs for real-world tasks that involve long-form content, such as book summarization, code generation over large repositories, or maintaining lifelong conversation histories. Overall, this paper demonstrates that with innovative data generation and training strategies, we can push the boundaries of what LLMs can handle, making them more versatile for complex, real-world applications.